In this lesson we're continuing with Exponentials and Logarithms B, and we're going to look at the first of two videos in experimental data and linear models. Now, when you carry out an experiment, the results may show that there is an exponential relationship between the variables. So one of the variables may have a rapid increase or a rapid decrease. And sometimes this rapid rise or decrease can make it difficult to interpret the results of that experiment. So examples of these types of experiments basically might be bacteria in a sample over time, rabbit populations over time, and energy produced by earthquakes. Now, if we use logarithms to convert these exponential graphs to linear graphs, it can actually make it easier to find the relationship between the variables and to find our unknowns. So let's take a look at an example, or actually a proof first, to see what we really mean. So firstly, we're going to look at polynomial equations of the form y equals a times x to the power b. So if we take y equals a times x to the power b, and I previously mentioned we should be taking logs of both sides of the equation in order to try and make this exponential equation linear. So taking logs of both sides will give us log to the base 10 of y equals log to the base 10 of a times x to the power b. Now we've got this a times x to the power b as our argument. So we've got a product as part of our argument, which means this can be expressed as a sum of separate logarithmic terms, which is log to the base 10 of a plus log to the base 10 of x to the power b. Now if I focus on this last term here, I can see that the argument has a power, so that can come down and act as a multiplier for log to the base 10 of x, like so. And I'm just going to rearrange this a minute, because what I can see here is I've got an equation in the form y equals mx plus c now, which is obviously a linear equation for a straight line that we are familiar with. You can see there that my y is actually log to the base 10 of y. My gradient is b. My x is log to the base 10 of x. And my y-intercept c is log to the base 10 of a. So let's try and picture what that actually is. Instead of an x and y axis, I've got two axes, log to the base 10 of x and log to the base 10 of y. Okay. Now remember, I've just written log x and log y here on my axes. Remember, we always assume that it's log to the base 10 because we work in base 10. And I've got a y-intercept of log to the base 10 of a, and remember it's a straight line, so I might have something like this, obviously, if my gradient, that's b, was positive. So what I can see here is if we've got y equals a times x to the power b, then the graph of log y against log x will be a straight line with a gradient b and y-intercept log to the base 10 of a. So this can be quite a lot to get your head around, and these do tend to be A-B questions in the exam, but let's try an example and see how we get on with that. So the results from an experiment were noted as follows. So we've been given a table. It involves log to the base 10 of x and log to the base 10 of y. So basically we would have had other results, like raw data from the experiment, but what the question has given us is that raw data and the logarithm has already been taken of that raw data. So we've got log to the base 10 of x, those four values, and log to the base 10 of y, and those four values. And you can see that the values here aren't much different from each other across the two rows of the table, whereas before the logarithms were taken, those would have differed greatly. And that's why it would have been difficult to understand the relationship between the variables x and y. The question then goes on to tell us that the relationship between these data can be written in the form y equals a times x to the power b. We want to find the values of a and b and state the formula for y in terms of x. So before the logarithms were taken for this data, so before this happened, the graph would have looked something like this. And then we took the logarithms, and you can see that we actually have something like this if we plot the points. So that then represents that linear relationship, and it's much easier for us to work with a linear relationship than an exponential relationship. So our solution then, we're already told that we can represent the relationship between the data in the form y equals a times x to the power b. Now we've previously looked at this. Obviously we can take the logarithms of both sides, rearrange all of this, and we can get it into the form y equals mx plus c, where y obviously is log of y, m is b, that's the gradient is b, x is log to the base 10 of x, and c is log to the base 10 of a. So you can see here this graph that I've already drawn. The horizontal axis is log to the base 10 of x, the vertical axis is log to the base 10 of y. So my gradient then, I'm going to take 2 points here. I can take any 2 points from the table and calculate my gradient. Okay, so it's log to the base 10 of y2 minus log to the base 10 of y1 over log to the base 10 of x2 minus log to the base 10 of x1, as you can see from the table here. So we've got 1.67 minus 1.33 all over 2.29 minus 1.70. That gives us 0.34 over 0.59, and simplifying will give us 0.58 to 2 decimal places. And remember, b was the gradient. Okay, so that means that b here is 0.58 to 2 decimal places. And that was one of the questions we were asked to find the values of a and b. So I've managed to find b here. Now, let's go back to this equation here. So log to the base 10 of y equals b times log to the base 10 of x plus log to the base 10 of a. Now I already have a value for b. I have 4 sets of values for log to the base 10 of y and log to the base 10 of x. And that should then allow me, if I substitute in here, it should allow me to find log to the base 10 of a. So I'm going to use the first column in my table here, or the first, well, it's really the second column in the table, but the first part of the results from the experiment, where log to the base 10 of x is 1.70 and log to the base 10 of y is 1.33, as you can see here. And I've also substituted in b, which I found to be 0.58. Now I can start evaluating the right hand side. 0.58 times 1.70 is 0.986. I can then subtract my 0.986 from both sides of the equation, and log to the base 10 of a is equal to 0.344. A is equal to 10 to the power 0.344, using basically writing my logarithm in exponential form. Putting that into my calculator gets me that a is equal to 2.21 to 2 decimal places. So I've answered the first part of my question. It told me to find the values of a and b, and then it asked me to state the formula for y in terms of x. Well, I know that y is equal to a times x to the power b, so y must be equal to 2.21 times x to the power 0.58. So just now it would be a good time to pause the video and copy this note down. You can complete the assigned exercise for today, and remember that there is a second video on experimental data and linear models.